on this next examples of Bernoulli's equation series on our channel, guys, we're gonna try to solve, answer, and explain this problem wherein we're given with a pipe that is inclined 10 degrees and has a water flowing through it. Of course, there is a pressure right here because it's inclined and going upwards. We don't know where's the source, but we're just given with this information that there is a pipe like this one, and here water is being discharged on this point. Also, we're given with the density of the fluid moving through it, and it says it's a water that has a density of 998 kilogram per cubic meter and has a viscosity of, that's kinematic viscosity of 1.005 times 10 to the negative 6. So it's a very small value for viscosity, meter square per second. So that's the kinematic viscosity, right? And then this one, the diameter of this pipe from this point isn't changing, and that is 0.006 meters, I guess, because we're given with 0.6 centimeters and I just convert it already to meters. So 0.006 meters in diameter of that pipe. And also the length of the pipe we're gonna analyze is 300 meters. So if you think about it, with this very long pipe, of course there will be energy losses. The energy here will no longer be the energy here because some of it has been converted to some other forms. So that's what they say, that's what they call head loss due to friction, the friction because of the pipe's length. Because if you imagine that very long pipe, of course there will be losses, and that's why we're given with viscosity, kinematic viscosity, that we're going to use later on. So other parameters that's given here is the flow rate. So the flow rate, volume flow rate of the water passing through this pipe inclined 10 degrees with respect to horizontal is 0.34 liters per minute. And if we convert this to meter cube per second, this is going to be 0.34 liters. We know 1000 liters is equal to 1 cubic meter, and we wanna convert this minute into seconds, so we multiply 1 minute to 60 seconds, and now these liters will cancel out minute. We're gonna left with meter cube per second, and it's going to be 0.34 over 1000 times 60 meter cube per second. So this is our Q, right? We're still on the given part, and then the question is if the pipe discharged to the atmosphere. So that's why here this is open to atmosphere. Determine the supply pressure. Whenever you have a problem like saying it's open to atmosphere, right on that, right away we can say that the pressure in this point is 0. That's a key there. Determine the supply pressure. So what's the pressure right here? We're being asked what's the pressure here. Determine the supply pressure if the tube is inclined 10 degrees above the horizontal in the flow direction. So the direction of the flow is going up the incline. All right. So now we have all of this information. What's the first step? Of course, let's apply Bernoulli's equation between these points. Right? Say this is point 1, this is point 2, discharge point. Then we need a reference. We take this as our datum line, the reference point, and the elevation of the first point is gonna be 0, while the elevation of the second point is just, we can solve through trigonometry. So we're given with angle, with the hypotenuse. You can see this is a triangle. So this is going to be 300 sine of 10 degrees. You can solve it of your own if you want. Sine of 10 degrees is the opposite side over hypotenuse, and so the opposite side is going to be 300 sine of 10 degrees. Now, applying Bernoulli's equation and considering only the major loss, or the loss due to friction, and not the minor losses due to pipe fittings or something like that. Only the major loss we're gonna consider. Then we're gonna have P1 rho g, the Bernoulli's equation, B1 squared over 2g plus HP due to pump, P2 over rho g plus Z2 plus B2 squared over 2g plus head due to turbine plus head loss. Right away we can say there is no pump, so that term will cancel. There's no turbine. The elevation at point 1, since that's the reference point, is 0. And also at point 2 on this term, and also here, there's no pressure acting to that because it's open to the atmosphere. So P2 will be 0. Our elevation on this point is equal to 300 sine of 10. And what other else? Of course, we're looking for this one, so we're not gonna cancel that. We're just gonna write it down, rho g. And then, of course, the head loss, because we're gonna consider that because we're given with viscosity. We're gonna use that later on. So now if we think about these terms here, alright, we analyze point 1 to point 2 and observe that the pipe diameter is uniform, right? Let me ask you, does the cross-sectional area of the pipe change? If not, then with the velocity within it will change. Does it change? Well, we can see, or we can prove that V1, or the velocity, will not change between these points through what they call continuity equation. Just basically it basically follows the law of mass, conservation of mass, right? And so the flow on first point is equal to flow on the second point, and so A1 V1 is equal to A2 V2. Since the diameter of the pipe doesn't change, of course, its cross-sectional area will also not change. A1 and A2 is equal to each other, so we can just cancel that out on this equation and say V1 is equal to V2, right? Right away from that, we can conclude that the velocity are the same, and so we can just cross it out on our equation. Since these two are equal to each other, we subtract these exact terms on both sides and they will just disappear. Alright, so now we're left with this term, and this is what we're looking for. We've been asked what's the pressure on the supply, or in this point at point 1. Now the only thing that's hindering us to continue is the head loss here. We don't know what's the head loss, but I can tell you that the head loss due to friction is just basically FLV squared over D2G. So now we're adding another term here. What is this one? What is that term? What's the meaning of that? What's that all about? I can say that this is what they call Darcy-Weisbach equation. It is used to find the head loss due to friction with the parameters: friction factor, length of the pipe, velocity of the pipe, diameter of the pipe, and acceleration due to gravity. The only thing that is more like harder part of the head losses, or the major loss here, is this F term, because we don't know what's the friction factor, because pipes varies, right? The friction, of course, varies. There's no uniform friction in the pipe. So there is an equation we can use to identify how are we going to solve this F term here. And they said that if the flow, and now it depends on the flow, if the flow is laminar, then we can basically find F by just dividing 64 over Reynolds number. So now, unsa naman po ning Reynolds number? We have F, we have Reynolds number, there's a lot of things to consider, ba? But let's go back to Reynolds number later on. So laminar, that's the first case you wanna consider if the flow is laminar now or if the flow is turbulent. So I'm gonna explain later on what's laminar and turbulent, but for this, let's just skip it first and take these two cases. If it is turbulent, to find F, we need this equation. They call it Coolbrook-White equation, and this is equal to 1 over square root of F negative 2 log base 10 of the relative roughness over the relative roughness over 3.7 plus 2.51 over Reynolds number times square root of F. Now with these two cases, we can find the friction factor because if we found out what's F, then we're good to go, right? We can now find what's the pressure. But for now, let's first know what's Reynolds number and this relative roughness. This is due to pipe, right? This is all due to pipe. Now for the Reynolds number, again, to find the F, we need the Reynolds number. Again, let's go back. To find the friction factor, we need Weisbach, Darcy-Weisbach equation, and this is FL, B squared over D2G. And to find what's F, the friction factor, we need to determine first if the flow is laminar or turbulent. And to know if the flow is laminar or turbulent, we have this Reynolds number. So they said that if the Reynolds number is greater than 2000, then it is turbulent. The flow is turbulent. If the Reynolds number is less than 2000, then that is a laminar flow. So don't worry guys, I will link a video down below showing you what's laminar flow and turbulent flow on another channel because they have a good representation, good animation of it, good picture of it. For now, this is what I can give you here first. Now, they said that if the Reynolds number is greater than 2000, it's turbulent. If it is less than, then it is laminar flow. But how can we know? How can we solve Reynolds number? To solve Reynolds number, we have this equation. Reynolds number is just the diameter of the pipe times the velocity over the kinematic viscosity. That is why we're given with kinematic viscosity here in the first, because we're gonna consider the major loss due to friction. Or other forms of Reynolds number could be rho dV over dynamic viscosity. So these are all viscosity terms, and it forms like this one because kinematic viscosity is basically dynamic viscosity over density. Alright, that is why it looks like that one, right? Alright, now let's find out, let's solve what is the Reynolds number based on our given. So as you can see here, the diameter of our pipe is 0.006 meters. That's our first parameter. The D, the velocity, what's the velocity of our pipe? For this term right here, that's the velocity, and for the below, that's kinematic viscosity. So our kinematic viscosity is 1.005 times 10 to the negative 6. 10 to the negative 6. And what about our velocity? Do we know our velocity? I can say yes, because we're given with the flow rate and the diameter of the pipe. With that information, since we know Q is equal to AV, then V is equal to Q over A, right? And our A here is pi by 4 times the diameter, which is 0.006 squared. And our Q is the Q that we solved in the first part, which is 0.34 over 1000 over 60. 0.34 over 1000 times 60 cubic meter per second. So here, this is our velocity, or the velocity of the fluid moving here. So on our Bernoulli's equation, we cancel this out, because the velocity here is basically this velocity here, or this whole velocity here. It's just that the velocity is the same, so it gets cancelled out on our equation. Doesn't mean that we cancel this out, the terms velocity, because it has no velocity. No, that is not the case here. We have velocity, we know the velocity, and it is the same all throughout this length of pipe. That is why we cancel it. Alright, I hope that's clear. And so we have this velocity. We're gonna just substitute that here, and now we can find the Reynolds number as Reynolds number is equal to 1197 unitless. And as you can see, this number here is less than 2000. So now that we found out that the Reynolds number on this type of flow is less than 2000, this one less than 2000, then we can say this flow is laminar. Otherwise, if it's greater than 2000, then we're gonna use this equation here. Alright, that's the only part of Reynolds number here that we want to know, so that we can know what F or what equation we're gonna use. Since this flow is laminar, we're gonna use this to find F, and we already know what's F, and that is 1197. Right away we can solve for F as 64 over 1197, and that is 0.0535. Alright, since we already have F, this value, we can plug that here. Alright, on our equation, right, 0.005. We know that the density of water given to us is 998. The acceleration due to gravity is 9.81. The F, we already know what's F, so that's 0.0535. The length of the pipe we're analyzing is 300, and the velocity is this one, or the terms 0.34 over 1000 times 60 all over pi by 4, 0.006 squared, then squared. That's the velocity term all over diameter, which is 0.006 times 2 times 9.81. Now, the only unknown is P1. So, pressure at point 1 that we're asked to solve is equal to, the pressure at point 1 is going to be 563,640. Of course, Newton over meter squared or pascals. Alright, so this is now the answer to this particular problem. Right? Again, it's just Bernoulli's equation. We just analyze what's the pressure head, velocity head, and kinetic or potential energy head on points 1 and 2. And of course, consider head loss, because we're given with the kinematic viscosity, and that is related to the pipe, and all of that stuff until we get here on the Darcy-Weisbach equation to find the major loss due to friction. And then to find what's the friction factor, we need to first determine what type of flow. If it is laminar or less than 2000, we're gonna use 64 over Reynolds number, and if it is turbulent, we're gonna use Colebrook-White's equation and see what's this one. And then if we found out what's the Reynolds number based on the diameter, velocity, and viscosity of the fluid, we can now solve for F. And if we know what's F, we just go back to our main equation and solve for what we wanna know. That's it for this video, guys. I hope you got something here. Like, share, subscribe, hit the notification bell. Thanks for watching. Peace out.